Okay, so I'm going to start with the top one here. And bless you, since I'm given hydronium concentration, I would solve for the pH right away. Remember, that's the negative log of this 0.000125 number. Typing it into your calculator isn't the issue that when you probably had a little struggle on what sign I'm hoping. It is where in the world do we round off that number? So, the incorrect answer, let's start with that, based upon sig digs, would be 3.90. In my mind, it is hard to figure out sig digs with logarithm unless you put it in scientific notation. After all, the entire point of logarithm is it's a power of 10 scale. The entire point of scientific notation is it's a power of 10 way of writing things. So what I would do is figure out what this is in scientific notation. 1.25 times 10 to the negative fourth. And again, if you're unsure how to do that, I moved my decimal 1, 2, 3, 4 spots to get that into a number greater than 1, less than 10. Why I would do that is the number for the power of 10 corresponds to whatever you have in front of the decimal. And this is what made the very last WebAssign question a little tricky, because it gave you a number like 0.45. And you ended up with a pH of 13 point something afterwards, but it was hard to figure that out because you normally wouldn't put that in scientific notation. So if the first digit here corresponds to that, that means I should have 3 digits after the decimal. So that gives me my last digit here of 3. 3.903. At least that's what I had when I typed into the calculator. Okay, I personally, after I know the pH, I would solve for the pOH. Again, you can do whichever method you want. I could easily see students doing hydronium times hydroxide equals 10 to the negative 14th. And quite frankly, the advantage to that then is when you round off your numbers, you're doing the same rules of rounding that we've taught you since Chem 1. Multiplication is the number of digits. But I'll do pH plus pOH equals 14. The rules for add and subtract state whatever place they have in common last. And again, we're not going to base that off the 14. We're going to base it off the measurement, the 3.903. Which means when I take 14 minus 3.903, you are technically gaining a digit, because now it gives you 10.097 as the pOH. But in adding and subtracting, the important part is how the last digit is in common. Now again, when solving for the hydroxide concentration, you could do hydronium times hydroxide equals 10 to the negative 14th. I'm just going to do the inverse of the logarithm function. So hydroxide would equal 10 to the negative pOH, which is 10 to the negative 10.097. Now, if I do that, again, you're going to get a long-winded number. However, this number in front of the decimal is referring to the power of 10. How many zeros are in front of it? Like I had 3 zeros in front of my initial molarity of the HCl. That's going to tell me the 0 part. Those 3 digits after the decimal, those are the ones that are telling me how many digits I should have in my answer. Now, I'm not sure how yours was rounded off. When I did this, mine was 8.00. Maybe you had a 7.99 something instead. And then my power of 10 was to the negative 11. And if you recall, if you were to do hydronium times hydroxide equals 10 to the negative 14th, there's only 3 significant digits in the original molarity, the hydronium. Therefore, I should only have 3 significant digits in the hydroxide because the rules of multiply and divide the number of digits they have in common. Is there a question on any of this first problem? And there's 2 things different then if I extend the page to go over the second problem. One is I only gave you 2 digits of significance. The second is it's a base. So in other words, I already know my hydroxide concentration. And for the sake of helping me out with sig digs, I'm going to rewrite that in scientific notation. 7.4 times 10 to the negative third is my hydroxide concentration. Again, you could do hydroxide times hydronium equals 10 to the negative 14th. I'm instead going to start with the POH, which is the negative log of the OH. Remember, when you're doing the logarithm, that number in front, when you get your final answer, is based upon the power of 10. The number of places after your decimal place is based upon that number in front. I know it's kind of weird because then when you do the opposite, it's the exact opposite. So, .2 what? 13? I know there's a lab that we are going to be doing after spring break where half of you are going to have an acid, half of you are going to have a base. And remember, we only measure pH, so we'll have little pH meters that you're going to be reading a solution every now and then for. And we're going to ask you something at some point, and a lot of students that have the base are going to assume that they have the acid. So then their numbers are going to be off by 1 step. And that's where when you're given a base like in this problem, you have to be aware if you wanted to solve for the pH, pH plus POH equals 14. So now I can solve for my pH by subtracting this from 14. And if I subtract that from 14, 11.87. And lastly, again, if I were to solve for the hydronium, I do 10 to the negative pH. And once again, a reminder when it comes to sig digs, 10 to the negative 11th part, so the beginning, is telling me my power of 10. How many zeros am I going to have in front of this number? The 8-7 part is what's going to be in front of my value when I start. That's my actual significant digits. And if you're unsure of that, recall that the original problem only had 2 significant digits to it. So it makes sense if we were to do hydronium times hydroxide and use multiplication, I should have 2 sig digs. And that's why some of you might prefer to do that route of hydronium times hydroxide equals 10 to the negative 14th to keep track of sig digs a little bit better. So when I do this, I get, what is that, 1.3 times 10 to the negative 12? All right, so we're not going to get into the equilibrium part today, but rest assured, strength and equilibrium go hand in hand with one another. I guess the only equilibrium part you're going to see today is the double arrow I'm going to start bringing out again. Now, remember, An acid is something that donates that H+. We're usually going to stick with that Bronsted-Lowry definition of it's donating a proton. Remember, if it's donating a proton in water, it makes that hydronium ion, the H3O+. That's the Arrhenius definition. At the very end of the reading guide you did last class that introduced the Lewis definition of acid dealing with accepting a pair of electrons. We're going to avoid that right now for a little bit. We will have to come back to that at some point, but we were going to avoid that a little bit. You just did a calculation a little while ago with hydrochloric acid. What makes hydrochloric acid an acid is the fact that it can make that hydronium ion, that it's losing an H+. So we look at the formula HCl and say, oh, the HCl. But it's not really the HCl part that we have to worry about. Because if hydrogen stayed covalently bonded to chlorine, it wouldn't be that bad. But once that hydrogen is lost, that's when it carries those acidic properties that we went over last time. That's when it's now dangerous. That's when the pH drops. So really, our concern isn't the reactant HCl as much as how much of this H3O+ does it make. That's what makes the acid dangerous, because there's a lot of compounds that have hydrogen bonded to them. If they can lose that hydrogen, they are acidic. If they hold on to that hydrogen, they're just something with hydrogen. What we have to introduce today is that not all acids are the same. Some are strong, and I would suggest towards the end of today, next class period, you just having a general idea of which ones are strong, and maybe we'll kind of go over that at the end of the hour. But most of them are actually weak. That's why I'm showing the double arrow. Acetic acid is a good example. And I already told you that we keep vinegar in the classroom in case we spill a base, because the vinegar is an acid, it's acetic acid, and it can neutralize a base, and yet it's still fairly safe. I mean, you buy it in a thin plastic jug. People use it for cooking. I use it to clean a humidifier to get the calcium deposit off of it every week or two, because we have fairly dry air in our house and my skin cracks all the time because of it. This is acetic acid in water. Some of it will create hydronium and the acetate polyatomic ion, but some of it will stay as reactant. So you're going to have both species present, reactants and products. And our goal today is to do a few things with something like this. Recognize which things are weak and which things are strong, which again, hopefully that POGO packet will go over. Directly after notes here, I have to go over labeling things as conjugate acids and conjugate bases. Somewhat similar to labeling things reduced and oxidized and reducing agent and oxidizing agent from electrochemistry. Well, there's just some common vocabulary we have to go over. And then this will lead us into next week when we start doing mathematics with this. Okay? So, acids donate the hydrogen. You could have a weak acid, you could have a strong acid. Same thing occurs with bases. A strong base will dissociate to make hydroxide. For example, sodium hydroxide, the example I gave you for the calculations to start class, is a strong base. A lot of ionic bases are strong because a lot of ionic compounds completely dissociate in water, especially if that ionic compound contains hydroxide. However, there are some bases that are not able to completely dissociate. Ammonium hydroxide is a good example. Ammonium hydroxide will partially break down into the ammonium ion and the hydroxide ion. And again, what makes the base dangerous? It's the hydroxide part. If you have a compound that holds onto the OH, it's not that bad. Again, water has HOH in its formula. Water is hydrogen hydroxide. It is amphoteric. It can act like an acid, it can act like a base. It just depends on what it's around. So what would make that more dangerous is that OH that's produced at the end. And when you have only a forward direction arrow, That's a strong acid or a strong base. But once you see that double arrow, that's your indication that's not completely dissociating to make hydroxide. If it's not completely doing it, it's weak. And what we have to again introduce is that there's varying levels of weak. So in general then, again, the stronger you are, the more product favored you are. That's all that this statement is saying. And therefore you create more ions. Remember when I talked about properties of acids and bases, one of them is they can conduct electricity. Well, again, electrolyte solutions are solutions that contain ions. Strong acids and bases are good conductors of electricity. That's why sulfuric acid is the electrolyte solution in a car battery, for example. We would typically not choose weak acids or bases for that job, although they would conduct electricity, just not as well, because they don't have as many ions in solution. So this goes over what I wanted to start off with today, dealing with strength. My last slide is going over that labeling of conjugate acid-base pairs. This was something that was briefly introduced in the reading guide last time. Again, you have a worksheet that you picked up on the way in that goes over this as well. I told some of you could write on the back side of it when we did our pH practice problems. So I want to quickly go over this, and then that is our notes for the day. One of the things that we have to be able to do is look at an equation, like any of the equations I just showed you to start off this set of notes, and be able to identify which thing is acting like the acid on the reactant side, which thing then is acting like the base on the reactant side. But then we also have to look at the products, in particular for these equilibrium style acid-base reactions. Because if it's an equilibrium type reaction, or dissolving process if you prefer that term, the products can reform reactants. The products can do stuff as well. And what you're going to see in probably about a week and a half is knowing this vocabulary is important for us. Important for us to be able to identify in something called a buffer solution why, when I added the acid and the base together, did it not actually make it to a neutral setting. So, what I have here is the conjugate base is the product of the acid that remains after losing a proton, and then vice versa, a conjugate acid is the product of a base after gaining a proton. Today you are going to do a POGO packet that's going to talk about the strength of acids and bases. And as we all remember, when I asked you to do a little bit of naming over the summer, I introduced to you acid naming. And there are 3 types of acid namings. 2 of them involve polyatomic ions. Like sulfuric acid is the sulfate polyatomic ion with hydrogens. Sulfurous acid is the sulfite polyatomic ion with hydrogens. But then you have the things without polyatomic ions, like HCl is hydrochloric acid. Well, HF is hydrofluoric acid. It's a halogen, fluorine, just like chlorine is, with hydrogen attached to it. And what you're going to see today is hydrofluoric acid of all of the halogens with hydrogen. So you can have HF, HCl, HBr, HI. Of all of that column, HF is the only one of those that is a weak acid. And the POGO packet will go over why, so I'm not going to get into that yet. But again, as you're working on that, if you're unsure, wave me down. When I look at this, I recognize that the HF is acting as an acid. It has the hydrogen to start. It no longer has the hydrogen at the end. That means the water in this case, remember that water, depending upon what it's around, it can act as an acid or a base. It's going to accept a proton, making it the base in this case. If I were to label this entire equation, I would label the HF as the acid. The water in this case is acting as the base. The conjugate acid then would be the hydronium ion, H3O+, the base with the added proton. And finally, the conjugate base is the fluoride ion. So again, I feel that this is kind of similar to what was oxidized, what was reduced, what was the oxidizing agent, what's the reducing agent. Vocabulary that we needed to know to do electrochem, you're going to find that this vocabulary is stuff that we need to know as we move forward. I'll record this too. Up on the smartboard, I have the 3 most common strong acids that contain polyatomic ions. Perchloric, which is HClO4, nitric, which is HNO3, and sulfuric, which is H2SO4. Isn't that annoying? I had my phone on silent, but if I play music through my phone, the speaker's on, then it yeah, the smartboard is flickering. I'm sorry. I was looking at it before it stopped. So, perchloric HClO4, remember, there's polyatomic ions with HCl3, HClO2, HClO, but that's kind of that inductive effect. Nitric acid's HNO3, there is a nitrous acid, 1 less oxygen, less inductive effect, it's weaker. Sulfuric is H2SO4, there's also an H2SO3 sulfurous acid, less inductive effect. Now, phosphoric acid is sometimes considered to be strong, sometimes not, depending upon where you look. So heck, if you just Google online strong acids, sometimes H3PO4 pops up, sometimes it doesn't. So that's why I left it off this list. And then the halogen acids. Anything except for HF is going to be a strong acid, again, because that bond length is long, easy to break. So I wanted to kind of go over that. And then, I know Claire was already looking at the web assignment and had a question, so I thought I'd just address that with everybody as well to wrap up class here. In number 1, it says identify the acid-base conjugate pairs. Now, the only issue that I have with this question is it doesn't use the adjective conjugate at all, but you're looking for which 2 things are pairs of one another. For example, in this first one, I would know HCN is an acid. And after it loses its hydrogen, here is its conjugate pair, the Cn-, its conjugate base. So I would make sure to click the box that labels HCN as an acid and Cn- as its base. I apologize that WebAssign did not use the word adjective for this. I'm sorry, the adjective conjugate for this. Although I believe after the first question, it's going to ask you to type in the formula of the conjugate acid. Make sure we subscript if we have to, superscript if we have to. So formatting is an issue sometimes with this. You had issues with SIGDIGs last time. Now it's how you type in stuff. And then the last one is just identifying, do you think this is strong or weak? Okay?